good afternoon. My name is Robert Jackson. I'm a structural engineer at Fast+Epp in Vancouver, BC, Canada. And I'm here to talk to you today about the TallWood House at Brock Commons. Specifically, a portion of this building, which is up for the Innovation Award, but just a comment here that this is currently the tallest mass timber hybrid building in the world. It's soon to be eclipsed by a 24-story timber tower in Vienna and a 18-story in Norway. But this building here currently holds that title, and it is driving a change in the building codes as to how we change those and the perception around fire and timber and building taller with timber. So this building here has a significant win off the fact that it is the tallest timber building in the world currently. But I'd like to dig deep into some specific innovation about that timber design and why that will really change certain market sectors and ways we build buildings in timber. I'd like to take you through just a general project overview so you get a feel for where this project came from and how it became designed, then really dig into that innovation and what's specifically unique about it, and how that impacted the construction sequence, both in terms of erection and speed and in just logistics. And then I'll wrap up with a conclusion on how this innovation can really drive certain market sectors moving forward. The design team, it's at the University of British Columbia, so they have a properties trust. They brought on board Acton Austria Architects, who is an incredible local architect, but they teamed with Herman Kaufman, who's one of the best timber architects in the world, I would say, and he has much experience with going taller with timber over in Europe. So he was brought on to our design team as a tall timber advisor. In addition to those two heavy hitter architects, they also brought on Urban One Builders, who is the CM for input right on early. They also brought on Seagate Structures, which is the timber installer. So they were there at the design table from day one to help us understand and help develop how we're going to put this building together. They also brought on great code consultants to exceed the building code limitations by quite a bit, and also a third-party 3D coordination consultant. In terms of timeline, we were brought to the table in December 2014, and we had 10 months to get this building in the ground, which included a very complex approvals process and a tender, and we had to get pouring foundations in 10 months' time. So it was very, very quick. To help offset some of that rush and that fast tracking, we were given external funding from the National Resources Canada, NRCan, Forestry Innovation Investment, Binational Softwood Lumber Council, and the Ministry of Forests. And this funding was used to help offset all the research and testing that we had to do to prove to the authority having jurisdiction that tall timber buildings are in fact a safe solution. One of the main driving factors behind this project is the notion of cost. The university had a building, a student residence building, 400 beds or so, that was built on their campus in concrete for $192 a foot. And that's very cheap for those who aren't in the construction industry. It's quite a cheap building, and that's in Canadian dollars, so you guys get 25% off anyway. The brief was, we have these suites in here, we have these student residences with a bed and a shower and a kitchen, and we know that this works, we know that we can lease these very well. We want to use the same typology, but we want to do it in timber with a different material, and we want it done for the same price, $192 a foot. And that was a very steep challenge for us as structural engineers, because timber buildings are perceived, at least, and have been proven in the past to be a little bit more expensive than concrete or steel. So we were given a mandate, come up with a design that is as cost competitive with concrete as possible. And in terms of building code, we were restricted to 6 stories with the British Columbia Building Code, which is similar to your 6 stories for type 4 with business occupancy in the International Building Code. But we know that we could move forward with UBC because they were an independent jurisdiction. They're sort of their own mini municipality. And they ultimately decided to get the British Columbia Safety Standards branch involved, which is the branch of the government that extends building codes to certain municipalities for their use. They did tons of interviews with us, lots of expert panels, lots of discussion around fire and structure, and they ultimately gave us what's called a site-specific regulation, which is an amendment to the building code for your specific project, for your specific site. Essentially, amending certain clauses such as you may not use a combustible material in a non-combustible classified building. So that's how we were able to get this building built and ultimately achieve a building permit. In terms of design approach, in light of that cost factor that we were given, we wanted to develop a very, very simple kit of parts prefabricated system. Not full-on volumetric, but a kit that included the structure and the envelope in order to protect the timber from driving rain and allow for really, really fast erection during the summer months. That was our approach. It wasn't full-on modularity, but rather a kit of parts prefabrication. This is a slide that gives you a feel of what the building looked like in construction, but I like it because it strips back all the different layers that are the main components. There's 2 full-height concrete cores that were slip-formed up in advance of the timber. Then there's 18 levels of 5-ply point-supported cross-laminated timber panels that rest on glue-lam columns, and around the perimeter is a prefabricated timber facade. It is technically feasible to do this type of building, say 18-story student residence, with a timber core or say cross-laminated timber shear walls. However, we decided as a design team to climb certain mountains, because what's very common about tall timber concepts that you'll see in the news is that they often just end up being concepts. They don't often get built. So we wanted to get this thing built and pick our mountains with the authority having jurisdiction. So we picked a defined lateral system that could be built and provide them with the level of comfort that they need for the egress routes. However, we are moving forward as a firm to using this gravity system around the perimeter, which I will talk to you about in a minute about, paired with cross-laminated timber shear walls moving forward. In terms of plan, it's these panels, these CLT panels, point supported on glue-lam columns at an array of 8 meters long, 10 meters long, up to 12 meters long. So some of these things are 10 feet by 40 feet in length, and they're these prefabricated systems which fit very, very nicely on a flat deck truck. In terms of architecture, this is a very, very basic building. I'm not going to pretend that it's some masterpiece per se, but the programming is such that it's just a very simple doubly loaded corridor student residence building with studio suites off each corridor and quad units at each end. These are the spaces that the students need, and this is analogous also to social housing and very, very small multi-unit residential housing. So I'd like to speak now about the specific innovation on this job and how that really impacted the design and the erection of the building. It's this notion here of point-supported CLT. This system is what we came up with, which essentially is very analogous to two-way concrete flat plate, which is what most condos and most towers are built out of these days, either PT'd or not PT'd, but it's got no beams. And the fact that there's no beams for concrete flat plate is awesome, because they can run all their mechanical services underneath without having to duck underneath beams. That's why it works great. It also saves you a lot of money on the envelope because your structural assembly is quite thin. So we wanted to achieve the same thing but in wood, and that's how we did it here using cross-laminated timber panels, which have a two-way spanning capability. This is the first of its kind. There's never been much use of CLT in two-way spanning because it really hasn't been harnessed that much yet. Most CLT projects that you'll see in the news or to date are one-way spanning deck, essentially over top of drop beams. This here eliminates all the beams, harnesses the CLT in the way it's meant to be, I believe, because of the two-way material, and it allows for super fast erection because there's no beams to put up. As I mentioned, it's very similar to two-way concrete flat plate, and one of the issues we get with that as engineers is this notion called punching shear, and where that concrete column wants to punch through the slab, so we often deal with that by putting headed shear studs in or drop panels to increase the overall depth of the assembly. So if that's how that works in concrete, how does it work in our point-supported CLT system? It essentially creates this phenomenon called rolling shear, where you can see fibers of wood on the right-hand side, which are essentially spaghetti strands or straws stacked together. There's different types of shear, but rolling shear is where these strands want to roll across each other, and it's very, very weak in that capacity. Timber's very weak there. So not to hit this too hard, but on the top you'll see pure shear. You can imagine taking a knife and cutting through spaghetti strands. On the second bend, you'll have longitudinal shear where the strands slide across each other. And on the bottom is rolling shear where the strands roll across each other. And that was the stress typology that we were imposing by moving forward with a point-supported CLT system, and that had never really been researched in depth to date. So we had to take what research was available from Europe and do some assumptions, do a lot of finite element modeling to really fully understand the bending and the shear and the deformation and what was going on there. And we came up with a design of a custom CLT panel that we were comfortable with and we thought could withstand those forces. Then we ultimately decided to move forward with testing that assembly from three prospective suppliers. So if you wanted to bid the project, you had to do the testing with us. So 6 panels per supplier, fully loaded tests down to failure. And we saw some very unique failure patterns, which has really helped inform the timber engineering community as to what rolling shear capacities really are. So that was really what was unique about this system, and why, in my opinion, it hasn't been used to date, is because there's a lot of unknowns around rolling shear, but we've done a lot of analysis and testing to prove out this system. Another part of this system which is unique is the notion of this column-to-column connector, which had to be prefabricated in such a way that it allowed it to be erected as a kit, very quick, like Lego connectors. So what we needed to do is get the load from the column above into the column below without imposing any perpendicular compression stresses onto the CLT panels, because you'll just crush the wood. So we wanted to sit those panels on the side of that, on the side of the column, and have HSS spigots which fit them together. So along with this point-supported system comes this column-to-column connector, where you can see the column is standing there, the CLT sits on the lip, bundles of columns are stacked on the active deck, and then 3 strong Canadian guys lift them into place. Another part of this tall timber building concept in general, and this point-supported system, is the notion of axial column shortening. Essentially, if you push on something, it's going to deform. It's a very well-known structural phenomenon. But with wood, you also have to consider parallel to grain shrinkage, which is normally not a major concern, but 18 stories, you need to account for that. And we had concrete cores, so we needed to determine, okay, how much are the cores going to come down and how much are the timber columns going to come down? And what's the difference between those two, and how do we mitigate that so you don't trip when you come out of these elevators? So what we did is we did site surveying, and we put steel shims on the top of those HSS spigots to bring the top of column up above its theoretical design datum by that deformation amount, so that at some time later, after the deformation has taken place, the tops of the columns come down to their theoretical datum. Also, another major consideration with this building and point-supported CLT was the notion of prefabrication, and then accounting for all the service distribution and all the plumbing stacks and how those needed to be punched through those CLT slabs and the stresses around those. So we modeled all of that, and we made sure that those stresses worked. There was also a significant amount of prefabrication being done while the foundations and the podium slab and the concrete cores were being done in the winter months. This was also being done in a nice warm shop, keeping the timber dry. They produced nearly 1 million board feet in 2 months' time of cross-laminated timber panels. Coupled with that, they did it to incredibly tight tolerances that are needed for prefabrication. We did glue-lam to plus or minus 1 millimeter. We did CLT to plus or minus 1 millimeter across a 12-meter long panel, and steel to plus or minus 0.5 millimeter, which is far exceeding that of industry standards, but we believe is necessary for a prefabricated kit-apart system that's going to click together. Now, I'd like to talk about construction now, because this point-supported CLT system, which we came up with, I think really became clear as to why it's advantageous during the construction process. This is a typical floor, and I'd like to run you guys through this. On day 1, you get, again, those 3 strong Canadian guys, and you get them to hand bomb these columns up and stand them into place. Around the perimeter, those columns are installed by the crane. Then you need to plumb them off. You simply use that with these spreader bars, which get these columns perfectly plumb, and you also get them on grid. such that they can receive these prefabricated and machined CLT panels that are flying right off the truck in the perfect time and sequence and spin, so you don't have to spin it with the crane. You land these into place and you simply secure with a nut. And then on moving from left to right, you simply lay down a plywood spline, you stitch off the active deck while the rigging is going back down. It takes about 10 minutes to rig up a panel and put it in place. We've put in steel drag straps to drag seismic load out of that diaphragm into the concrete cores and install a perimeter edge angle, which was used to accept the prefabricated steel stud facade system, which went up in tandem with our timber system to protect it from driving rain and eliminate any need for crane work after the fact. So what that all results in is nearly 20,000 square feet a week. We did 10,000 square feet floor plates roughly every 3 days using a 7-man crew with 1 crane working 7.5-hour work days with coffees and lunches. It wasn't working through the night, but it's nearly 20,000 square feet a week, including envelope, which is quite a fast erection sequence, and why we think this point-supported CLT system is really worth considering on projects moving forward. So just a couple remarks in conclusion here. We've done a lot of mass timber buildings at our office, and based on post and beam and deck projects, past precedence projects, we estimated about 3,600 cubic meters of timber would be needed for this building based on this square footage. We achieved 2,200, which significantly drives the cost down for the supply, and it's just less pieces to deal with because we got rid of all the beams. Again, back to that cost mandate, we were given a mandate of $192 a square foot. In considering construction escalation, that's around $215 a foot for concrete. We did it for $235, so about 6% premium over a concrete alternative, not including the accounting for carrying costs and interest costs and things like that that would be of significant interest to a developer. We thought we could do maybe 1 floor a week, 10,000 square feet a week, including envelope. We did 2 floors a week. We thought it would only rain a little bit because we did it in the summer, and then it just poured rain the whole time, which is a story for another time. And we thought we could do it within 1 millimeter. You know, tolerances were very, very tight, and we worked hard to achieve those, and it is indeed within 1 millimeter. They have ran a tape across the width of the building, and it is very, very accurate. So this is a very innovative system that eliminates beams, this point-supported CLT system. It significantly increases the speed of erection and how you could put tall timber buildings up. Because it's a prefabricated kit of parts that includes the structure and the envelope, there's ways to scale this up with prefabrication by throwing in bathroom pods, kitchen pods, things like that. The 3D coordination and involvement of trades early really helped inform the design and was a big factor. Wider column grids are possible for this type of system, and we have developed one in our office off the heels of this project for applications in office and institutional grid layouts. But this system here in timber we think is very scalable and could be used for multi-unit residential buildings, social housing, you know, affordable rentals, hotels, things like that. This point-supported CLT system is very, very applicable for using timber in getting buildings built. That is a market sector ripe for change. A lot of the buildings like that in Vancouver are currently just built with 2x4s and 2x6s, up to 6 stories, 8 stories with concrete. We think that this system here could be used to revolutionize that market sector and really change social housing and multi-unit residential buildings for the future to be built out of timber. Thank you.